Hi there, how are you? We're going to talk a little bit about proving that two functions are inverses. So to prove that two functions are inverses of each other, we need to substitute the functions into each other and get x for both of them. So if I had two functions, let's say f of x equals 2x plus 4, and we had f inverse of x equals x minus 4 over 2. In an earlier video here, I actually went over taking this and solving and finding the inverse, which was this function. Now, to make sure that our work is done correctly and you want to prove that these two functions are inverses of each other, we need to substitute them into each other. So if they are to be inverse, f of f inverse of x must equal x. So I have taken my inverse function and I've substituted into f of x. And when we do all the work, if we get x, we are halfway there. We also need to do the opposite substitution. We need to take f of x right here inside and we need to substitute it into the inverse function, f inverse of x. If we do that and get x, then we are all the way done, and you have proved that f of x and f inverse of x are actually inverses of each other. Okay, should be known by the notation that they are inverses, but if you want to prove it and show it, here's how we take care of this. So we're going to do some substitution into each other. First, I will take f of x. So f of f inverse of x is 2x plus 4. This little separation right there. So I have my two functions. There's one. There's my inverse. So I have f of x, which is 2x plus 4. Where x is, I've left a big spot because we're not substituting in a value of 2, we're not substituting in a value of 8 or 9 or 50 or whatever it is. We're substituting instead in a function. We are substituting specifically f inverse of x, and f inverse of x is x minus 4 over 2. So coming through, if we're going to start to clean this up, first we will multiply 2 times this right here. Well, the 2's are going to cancel nicely and neatly when we do that. So we then end up with x minus 4 plus 4. Next step, the minus 4 and the plus 4 cancel out, and you are left with x, which is really what you want and what you need. So f of f inverse of x equals x. Halfway there. Now we need to do the other substitution, the alternate substitution, and we need to end up with the same value of x. So I will take f inverse of x equals x minus 4 over 2. That is my inverse function in purple right there, and I've left a spot to substitute in f of x. So instead of plugging in a value, we are plugging in a function. What function am I plugging in? Well, it is 2x plus 4. So 2x plus 4 goes where my x value is. So if we were to clean this up, first you're going to deal with your numerator, 2x plus 4 minus 4. Okay, if you were to distribute that invisible 1, your parentheses would drop. So those positive and negative 4's would cancel, and you would be left with 2x over 2. Breaking it down further, the 2's will cancel, and you are left with x. Therefore, f inverse of x, of f of x equals x. A little messy right there. And you can say that since they both equal x, yes, they are inverse. They're inverses of each other. So let's take a look at one more example of that. Give us a nice break right there. So let's deal with two functions. We have dealt with these previously. Let's do b of x equals x squared plus 1, and b inverse of x equals root x minus 1. Now for this function right here, b of x, to actually have an inverse, well, the inverse needs to be a function, and the way that we can make sure that the reflection over that x equals y line is truly a function, we would need to constrain this. X would need to be greater than or equal to 0. We could only use half of that parabola because the reflection would be a non-function parabola. Therefore, that would not be a function. So with those constraints, we need to substitute them into each other and we need to get x for both of those values. So I will start with b of b inverse of x. That is the inverse substituted into the function. Then we will do b inverse, of b of x. That is the function substituted into the inverse. That is how I get these things set up. Then we just deal with our substitutions. So first, I'm going to write out b of x, which is x squared plus 1. I left a big, huge blank where my x value is, and my inverse will get substituted in. There we go. We're going to clean that up in 1 second, but let's get my substitution set up over here as well. So now I'm going to take my inverse, which is root x minus 1, and I am substituting in the function, which is b of x squared plus 1. Okay, we're going to clean both these up. If we end up with values of x on both sides, we have proved that they are inverse. All right, so let's come on over here. First, I'm squaring. So the square with the root will cancel each other out, and you would be left with x minus 1 plus 1. Well, those parentheses drop when you distribute that invisible 1. So minus 1 and plus 1 cancel out, and you have x. So b of b inverse of x equals x, halfway there. Now we're going to do the cleaning up over here. Okay, let's see, what can I do here? Well, distributing that invisible 1 drops my parentheses. So inside my root, I would have x squared plus 1 minus 1. The plus 1 minus 1 cancel, and you would be left with root x squared. Well, now the root and the square cancel, and you are left simply with x. So b inverse of b of x equals x. And you can say, yes, they are inverses of each other, and we have proved it because they are both equal to x. Awesome.